Hi, and welcome to our video on the introduction to convolutional neural networks. So in this video, we'll discuss a lot about what makes convolutional neural networks so important to computer vision. So firstly, why are CNNs or convolutional neural networks needed? It's because neural networks don't scale well to image data. So remember how our images are stored in arrays? We have three-dimensional arrays like this for color images and two-dimensional arrays like this for grayscale images. So let's look at that. Remember we have this. So now imagine we had a simple image classifier that takes a color image with input 64 by 64. So now imagine now the input size to our neural network is going to be 64 by 64 by 3. That's how much different input values we have. So this is going to be a very complicated neural network. Imagine we went to 640 by 480. That's going to be 921,600 weight values. That's going to be a very big and massive network. It's going to be computationally very slow to calculate and train this type of neural network. So we need to take advantage of image data. And what is consistent in image data is that we have different patterns or different colors that are correlated. So that's a very important concept. Then there must be a way we can take advantage of this. And that's where convolutional neural networks take place. So this is what a convolutional neural network structure looks like, and we'll delve into each one of these in this video and what they do. But effectively, this is the convolution. This is what happens here, where it takes a segment of the image, extracts certain features or learns features in that section here, and then does a bunch of different things here that finally lead to our output. Now, convolutional neural networks take advantage of the three-dimensional volume of images, essentially, okay? So images consist of height, width, and depth being our RGB color components here. So if we treat our image data like this, like a three-dimensional array, which it is, we can effectively take advantage of a lot of the correlations within image data. So let's take a look at this now. So why 3D layers? As I just said, this allows us to use the convolutions to learn image features, and this concept allows us to use far less weights in our deep network, allowing for significantly faster and better training. So this is what the convolutional layers look like. We have our input here, which is our input image. We have our convolutional layer here. We have the ReLU layer, which is basically combined with this, just the activation layer. We have our pooling layer, which sort of downsamples the image here. We can have another convolutional layer with ReLU. We have pooling again. Then we have something called a fully connected or dense layer that leads to our outputs here. And the outputs being basically probability scores of what the object is in this image. So in this case, we can see it's not so much a panda or a dog, but definitely a cat, which it is. So let's talk about the convolutional layer, which is the most significant part of the CNN. So what exactly is a convolution though? Now, a convolution is a mathematical process or term that's used to describe combining of two functions to produce a third function. And this function is what we call our feature map. So a convolution is the action of using a filter or kernel that is applied to the input, and in our case, the input being our image data. And it does that to produce the feature map. The feature map is essentially pieces or segments of the image. So we'll take a look at this now. So what is a convolutional process? Remember I said a convolution is a mathematical term that produces a third function. This is our input. This is our convolutional matrix here, or kernel. And this is the output or feature map. So let's see how we apply this to get an output here. So now let's simplify this to ones and zeros here to make our life a little simpler with the calculations. So imagine we have this grid here, this 5 by 5 grid here of ones and zeros here, and this 3 by 3 matrix here with ones and zeros and a -1 here. So let's see how we can multiply these two to get our output feature map. So this is exactly what we do. We put our kernel over here and we slide it across one pixel at a time, or whatever we set it to. And essentially, this is the calculations it does here. So we have 1 by 0 plus 0 by 1 plus 1 by 0, and so on. This here, which gives us this here, which gives us the value here too. And as we slide it across this one here, we'll get a value for the third one. Slide it across this box here, we get a value for this. Move it down one. So you can see how by passing a 3 by 3 kernel over a 5 by 5 input layer here, input image, we get a 3 by 3 output. So this is exactly what we do. As I said, we keep moving the sliding around over and over and over. So what are the effects of the kernel? So depending on the values of the kernel matrix, we produce different feature maps. So applying our kernel produces scalar outputs as we just saw. Now convolving with different kernels produces interesting feature maps that can be used to detect different features. That's a key point here. Now convolutional keeps the spatial relationship between pixels by learning features over small segments as we pass over the image. So what does that mean? That means that you can go back to this here. If this is a 5x5 image here, and we get a 3x3 output here, where we learn some sort of thing from the image here, this is our feature map here, it basically keeps the spatial relationships, maintains the spatial relationships, I should say. So we keep it consistent. So whatever was in the top corner of the image here is still represented in the top corner here. Whatever is in the bottom corner here is still represented over here. So now, why do we need many filters and not just one? We can design our CNN to use many filters as much as we wish and in different sequential combinations. So now let's assume we use 12 kernels, or 12 convolutional layers here, okay? So this is a 28 by 28 image here, and this is our kernel here, and this represents here our output from each pass of this kernel here, or over the image, our output here, represented in 12 of these kernels here. And you can imagine them stacked like this together. That's how we envision or imagine our kernels that we produced, okay? So now remember I said we have ReLU and convolutional layers combined. What exactly is ReLU? And what exactly is an activation layer? So remember, in neural networks, what makes neural networks special or synonymous to our brain or neurons is that once it reaches a critical point, the neural fires. But what is that critical point? Well, let's look at this here. ReLU stands for rectified linear unit, and it simply changes all the negative values to 0, leaving all positive values unchanged. So effectively, anything that's positive, it fires. Anything that's negative, it basically clamps to 0. That's how it's represented in this function here. So by applying ReLU to this here, this is our output. It's quite simple. So that's what our activation layer does. This is how, after we produce our convolutional feature map here, we apply ReLU to it here. So that's how it moves forward. So what about pooling? Now, pooling is also known as sampling or downsampling, and it's simply the image process where we reduce the size or dimensionality of the feature map here. So imagine this is our feature map that we produced. Before it was a 3x3. In this example, it's a 4x4. And if we do something called max pooling, max pooling is typically the most popular type of pooling we use when building convolutional neural networks, this is what happens here. So this is what it's downsampled to. We just take the max value here. So all this time, you can see all our layers are doing is basically encoding complicated patterns, but sort of compressing it, okay? And by doing that, we're learning many different attributes of the image here, of our input images, and storing them as compressed, basically generalized detectors that fire on different reasons, okay? So now let's lastly look at the fully connected layer, also known as the dense layer, which you'll find out shortly in the code. Now, fully connected simply means all the nodes in one layer connected to all the outputs in the next layer here. The FC layer, which FC stands for fully connected, outputs class probabilities where each class is assigned a probability. So imagine when our cat example, we have 0.05, 0.04, and 0.91. All of this sums to 1. Similarly, in this example I use here. So now let's talk about overfitting. So we're finished with discussing the layers of this convolutional neural network. We're now talking about how we train and what's a good model in a convolutional neural network or any kind of neural network. So let's discuss the concept of overfitting. Overfitting is the concept where we tweak our model so precisely on our input data that it generalizes bad on new data. So this is an example here of classifying points from left to right here. All these blue points here in one class and all the green points here in the other class. But you can see that this point here, even though it's in the example data, it's here, generally you would want to consider this point to be in green. This is what an ideal balanced network looks like. And you might think this is a good network here, but what if this blue point was just slightly shifted here in new data? Is it still going to be blue? It should all be green given the cluster of data here. This can be an anomaly or mislabeled data. You don't want to learn too much on our training data so that these examples take precedent. You want to have a generalized network that's ideal so that it can treat new data quite well and give them accurate classes. Underfitting is now the opposite of overfitting, where we have a model that's basically too simple to generalize well on new data. Now let's talk about regularization methods. Now, regularization method is one of the ways we avoid overfitting. Now, overfitting is something CNNs and neural networks are very prone to, so we have developed many methods to sort of reduce or avoid overfitting. So the first one we look at is dropout. Now, dropout refers to just dropping nodes. Remember the hidden nodes and visible nodes we saw in our neural network? If you just drop out some of the nodes during the training process, we sort of find a way to not learn too much about the input data so that we can generalize better. Now, there's also something called L1 and L2 regularization, which are applied in many other machine learning algorithms as well. And what they do, they basically just penalize very large weights on our nodes so that we actually don't have extreme responses to certain input data. Also, we can look at some cross-validation, also known as k-fold cross-validation, which is a method of training where we split our data into a number of folds and train on them and then test on another fold here. So you can see we keep one fold, we hold one fold back, we train on these 4 folds here. This is our training data set here, all of this here. And then we just keep doing it by piece here. So effectively what that does is that we just keep one piece of the training data out of our first training loop or epoch. Now, another training method regularization method we can use is something called early stopping. So early stopping is a way we just set the parameters or some threshold criteria, typically loss. Once loss has stopped decreasing and starts to increase, we basically stop training at this point here, because what's going to happen is that we're going to basically, this is validation loss that we're looking at, or test loss. Sometimes test loss comes down gradually and this is good, but then if it starts shooting back up now, what's happening there is that it's basically overfitting on your training data and performing poorly or generalizing poorly on your test data or validation data. And lastly, a good method I find to use is data augmentation, where we just make slight variations in the input data like this, so that it sort of like magnifies or amplifies the amount of input data we have. So what have we learned in the video? We've learned why convolutional neural networks are better suited for image classification, how they are structured, their layers, their architecture, the purpose of each part of the layer, why overfitting is bad, and some methods of regularization that are used to avoid or reduce overfitting in convolutional and neural networks. Thank you. And now let's move on to the next video, where we take a look at creating a convolutional neural network using Keras and TensorFlow 2.0. So stay tuned.